Okay, so here, continuing with the bones. I did put this PowerPoint up last week, and of course I had to do a little bit of modification here and there, but the parts that I added on, they're very minimal, so I didn't feel like putting up another PowerPoint just because I added a couple of slides or some comments. So make sure you pay attention to the parts that I didn't change. Okay, very few parts. The whole thing basically is okay, but just a few comments here and there. And this part for bone formation is what usually gives people kind of a hard time, because no matter where you look, the sources are not showing you exactly what I would like to see, right? Which is really, you know, this 3D type of animation of bone formation, especially the ones that are coming from cartilage, right? I didn't find it yet. I'm hoping that now with AI, there will be some better sources to show what's going on. But I'm really doing like the best I can with the description here, and hopefully it's a bit more intelligible than what is in the text. Okay. So here we're looking at the microscopic analysis or anatomy of the bone, right? And you should definitely know which cells you have in the bones, right? Oh, also as a side note, remember that I made available all of my previous year's lectures. So in case you're having a question on whether I mentioned something here or whether we want to see explain a little bit of a different form, you can always go back to my last lectures and check out if the information is a bit better or not. Okay. All right, so things you have to know. You have to know the types of cells that you're going to find in the bones, right? Remember that you're going to have the stem-like cells, so those are your osteogenic cells. Once they become more differentiated, they become osteoblasts. So those are the baby bone cells. Then something happens, and the osteoblasts become more mature. They become osteocytes right there. So today we're going to see what is it that is happening for these osteoblasts to become osteocytes. Besides those cells, you also have bone lining cells, and those are going to be close to the membranes. They're going to be either on the inner part of the outer bone membrane, or they're going to be in the inner bone membrane. Do you remember the names of those? What is the name of the membrane that covers the bone? Periosteum. Oh, you're close. Peri something, but it's a pericardium that's covering the heart. Yeah, peri something is covering something. So instead of going cardio, it goes osteo. So it's periosteum. Remember, the periosteum has two layers of membranes. It has the outer, tougher layer, and it has the inner layer that has the osteogenic cells as well as these bone lining cells. Okay. So all of these cells here, they are coming from those progenitor cells that are in the bone, right? Now, when you look at osteoclasts, that's the other type of cell we have here. This cell will have a different origin than the rest of the bones, okay? So those are going to be derived from hematopoietic stem cells, from cells that make up blood cells, okay? So here, starting to look at those strange cells, right? So you have those osteogenic cells, and that is going to give rise to the bone cells, right? So these osteogenic cells, they are also called osteoprogenitor cells. So they're basically the same thing. Okay, those cells can divide, and they are present in those membranes that I just mentioned. Okay, they are present in the periosteum and also in the endosteum. Remember, the periosteum is the membrane that has two layers. Okay, it's on the outside of the bone. Okay, so let me see what is important here. Okay, so those are your stem-like cells, your osteogenic cells. Second type of cell, those are your osteoblasts. Okay, so those are beginning to differentiate into the bone cell. Okay, so those are going to, so this is starting the differentiation, not finalized, okay, going into the process of becoming osteocyte. So what happens here, you have some change in the genetic expression of your progenitor cells. And these osteoblasts, they start to make that matrix stuff. And specifically, they start to make this organic part of the matrix of the bone. So this matrix parts that they are depositing out there is called osteoids. Okay. What is it that's going to make up this osteoid mass? It's basically made up of two things. You're going to have collagen, so that is your protein portion of the osteoid, and also you're going to have mineral deposits. They're going to make the cement-like part of the matrix. Okay, so collagen is really going to be the predominant protein that you're going to find in bone tissue. If you look here, it's going to be like up to 90% of the bone protein is going to be collagen. Okay. So those osteoblasts, they can divide. Okay, they have space to divide, and they have reasons to divide because they are starting to build up the bone. They're starting to build up the bone tissue. And we're going to see also the reason why after they differentiate, they don't divide anymore. Okay, so those, they are called here resorption base. So you see little depressions on the bone. They are telltale signs of erosion. You call them resorption base. Okay. So here are depictions of what those cells look like. So these cells here, those are going to come from the bone lineage, right? They come from together with the other two cell types. Remember, this first one to get differentiated is your baby bone cell, so that's your osteoblast. And the shape of the cell is different than the progenitor cell that it came from, right? And this guy is the one that is depositing the matrix. So it's starting to put down the hard matrix around itself. Okay. When it differentiates, it becomes the osteocyte. When you look at the osteocyte, it doesn't have as much of the body as this cell had. So it lost some cytoplasm. And it also has those tentacle-looking protrusions here. And here is showing a little bit, but they are actually kind of long because they are going to communicate with cells that are living in other lacuna. Okay, so they are really placed in this hard little space without opportunity or without any means to get anywhere else, but they cannot stay totally isolated without any cell communication, from the other cells. So these protrusions here, they help cell-to-cell communication. Okay, so you can imagine as this guy is laying down the matrix, it is also forming those little tentacles. Okay, and at the same time, it is communicating with other cells that are doing the same thing. So they start to form those protrusions, and by the time that this cell gets stuck in this little lacuna, it did not lose the communication with the other cells. Okay, and they keep this communication by means of tight junctions. Okay, so it's not like they fuse into the other cytoplasm, but they keep this tight junction form of communication. All right, so those are the two cell types here. And then you have that strange little Pac-Man eating thing. That's your osteoclast, so we just call it a bone-eating thing. Okay, so this guy comes from hematopoietic stem cells. So those are your cells that give rise to all forms of blood cells, and they actually derived from macrophages. Those are the big eaters. Okay, so they are a way of fusion. And the product of macrophages. Okay. All right, so looking here at the microscopic structure of those compact bones. So there are several parts here, several little terms that you absolutely have to know. And I'm sure that you have seen this already in your labs, right? So this is not like first time you're looking at those terms, I hope. Yeah? Who doesn't have lab? One person. Okay, so that might be the first time you're looking at those terms. Okay, but you gotta know them. I'm gonna tell you exactly what you need to know, right? As usual. Okay. So here with your compact bone, you can also call it lamellar bone, okay? And you have some basic structural shapes to this bone. You're gonna have the osteon. The osteon is your basic functional unit of this bone. Each osteon is like a little straw, okay? Like a drinking straw, okay? Each osteon is gonna have a central canal, and inside of this central canal, so here is your central canal, which is your little straw of your osteon. Okay. Inside of the central canal, you're going to have blood vessels that go in, so arteries and veins that come out. You're also going to have a lot of nerves, and you're also going to have lymphatics. Okay, so blood vessels and nerves and lymphatics inside of this central canal. This central canal is also called the haversian canal. Okay, so this is one of the strange name that comes in the first, right? So haversian canal. Now, besides the canal, you're going to have other little channels that are not on this central canal. So this is the central thing. You're going to have other structures that are going to come around this canal, okay? And then you're going to have connecting channels. They're going to go like across this way, and they're going to cross that way. And those small canals, they are called canaliculi. Okay, so canaliculi are the little canals. Okay. The rings that form around this central canal, those onion layers, looking like onion layers, right? You're gonna call them lamella. Okay, so lamella for the onion rings. Okay. All right, so here you're gonna have your layers, like onion layers. Those are lamella. Okay, a lamella, you find them here, right? The little lakes that we're talking about, that's right there. So you're gonna find one cell inside of a little lake. And how many little lakes you're gonna have? Well, a lot of them. Here is another lake, here's another lake. So all of these tiny little lakes with only one cell inside, those are called lacuna, okay? Lacuna is one lake, you put the E, that's plural. So lacuna is still called lacuna. And when you look here at the little canals, they're going this way, they're going this way. You see that the cells are communicating through those canals. So those are your canaliculi, okay? Observe here that you have a lacuna, right? Lacuna on the ring, and then canals, little canals connecting them, both like across each layer of this onion and also around the little ring. And the word canaliculi always reminds me of Italian dance. Any Italians in the class? Yay! You know the tarantella? No? How Italian are you? Ma che? No? So there is a tarantella that goes like funiculi, funicula. You know? Never heard of it? Yamo, 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 yamo. No? You don't know how to dance the tarantella? Okay, you hold hands or you hold elbows and you go yamo, 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 enough dance. And then you say funi, funi, canalicula, funi, culi, canalicula, and that's how you communicate with each other, just by the hands holding. Okay? I don't know if it makes sense. Oh, so now you go start searching the tarantella. That's after class activity for remembering a bone microscopic structure. Okay, don't forget your canaliculi. Okay. Canaliculi, canalicula, it goes the same. All right, so enough Italian, right? So here looking at more of your haversian system. Remember your osteon is this thing, is this straw. One osteon is one straw, right? And that's very important for your very compact bone. Compact bone is not the one that looks like a sponge, okay? The one that looks like sponge is a spongy bone. So this guy is a compact bone, okay? Now, these cylinders, they are the little straws. You can imagine concentric straws. So you put one larger straw, you put a smaller straw inside of a larger straw, and you make the concentric straws. Okay, so that's what makes the layers of the onion, or onion straw type. Okay, so they are big cylinders, and they have these different layers. Now, if you look at the inner layer, you see these little lines here. So those are arrangements of your collagen fibers. So you see these collagen fibers are aligned this way. And then you see at the other layer, the collagen fibers are aligned the other way. And usually they hit at a 90 degrees angle. And then you see the other layer on top of that layer, and you see again a shift, 90 degrees shift from the inner layers. Okay, so this one here, the organization will look more like the second layer inside. And the reason for that is that the organization of those collagen fibers give a certain resistance or a certain strength to this osteon that has to do with twisting motion, twisting resistance. Okay, so when you twist your body, your bones are getting twisted too, and the reason why they don't break is because you have this interlaced or type of arrangement of those collagen fibers. Okay, so those are very important for resisting twisting. Okay. So here is a better picture of those canaliculi and also haversion channels, right? Haversion canals. Now you look, this is a hard bone. So this is the diaphysis of this long bone. Okay, so there's a piece coming from that side. Now you look at the inside part of this hard bone is not the same as the haversion canals. Okay, so the inside part, you're gonna see a spongy bone in there. So this inside hole here, you call that the medullary canal. Okay, so the inside is different than the hard bone. So this is a spongy bone. We are looking at those canals right here. Okay, so these guys here are the haversion canals. Okay, and then you have other types of canals. They are going to connect the haversion canal either to the center medullary cavity or canal, or to each other, like you see over here. So these canals are called penetrating canals, okay, and they actually run at 90 degrees in comparison to this medullary cavity right here. So they're going to connect either to the cavity or to other haversion canals, okay. Those perpendicular canals are also called Volkmann's canals. Okay, so this is why I put it right there here. Volkmann canal, a triangle to the central canal. Okay. All right. So here's another picture. This slide is the one like I was mentioning, I just added now because it had a nice picture here showing your Volkmann's canals. Okay. And it is showing you this osteon unit, right? And here I like this picture because it's showing you this canaliculi. Okay, canaliculi going that way, going this way, and you see those cells communicating by protrusions. They're linking one cell to another cell, and the linkage is done by tight junctions. All right, so another name for compact bone is also lamellar bone. Okay, we mentioned that. Okay. All right, so here I mentioned about the lacuna, and in the lacuna you're going to have your osteocytes. Okay, so I mentioned that. I mentioned here that they communicate by cell projections, and gap junctions is allowing communication. All right. So as we see, when you are forming the bone tissue and when the matrix starts to be calcified, when you start having deposit of hydroxyapatite to make this calcified tissue, you have those cells that totally get trapped. Okay. Now you can imagine how the process is happening. The analogy that I see in several sources is that let's say that you decide to clean your kitchen, right? So usually you sweep, but I forget about sweeping. So let's say you're going to mop the kitchen. So you start at one corner, and let's say that you have this idea that you're going to start from this peripheral area, and then you're going to work towards the center. So you are cleaning the kitchen, you start at the corners, and you clean the corners, and then you go more to the center, and more to the center, and you go all around, and then you find yourself that you clean everything, but there's a little area around your feet that you didn't clean. But then you get stuck in there because you don't want to step on the area that is clean to get to the other side. So let's assume that instead of just using cleaning products and water, you use cement. So you don't want to step on the cement, and the cement is going to harden, so you can't really get out of this little area. So this is more or less how these cells are working. When they're starting to deposit this matrix, the cells are your osteoblasts, and then when they get stuck, they find themselves in a place that they're not really getting a lot of nutrients from the outside because they just build a wall around themselves. They build this impenetrable wall, meaning that diffusion is not going to go through this wall. So they get very limited with their sources of food. How are they going to get food? Veins. Well, the supply is going to come from the blood, from the arteries, but the blood is not coming all the way to the canaliculi. You see, canaliculi is out here. Blood is over here in the center. And you don't have a lot of blood supplies, but basically they're going to share nutrients with the other cells by those tentacles they're going to get from there if they're not in direct blood supply. So they're going to ask you, the neighbor's like, hey, you clean your room and you're stuck in the center, can you stretch some food this way here? And then they go, okay, I ate from this side. He's like, and now I have waste products. He's like, hey, you clean your room, can you take my waste products over here? So they start communicating with each other because they have to get their nutrients, they have to get rid of waste products, and they're stuck in this hard place. Okay, so they're going to communicate by those canaliculi connections. Okay. Okay, so here it is. Okay, so we have communication with other osteocytes, and they're going to share nutrients and get rid of waste products by sending it like from one room to the next room, next lacuna, and then dump it into the venous circulation. All right. So here's this other nice picture showing your perforating canals and your center canal, haversian canal. Okay, and then you see, yeah, those blood vessels going through these perforating canals, but then when you look at the lacuna here, you don't really see blood vessels going there. So the guys that are close to the source, they're going to share the nutrients with the other ones that are farther away. Okay. And here's a nice picture showing the protrusion arms and the interconnections of those osteocytes. Finally, your first question. So here, a group of concentric rings of bone matrix comprising the functional unit of long bones is called, based on the PDF version that I put up. You should also have the answers because I had forgotten to take down the answer slides. So I'm assuming everybody's going to get this right if you have looked in at your PowerPoints, right? So 15 seconds. Five seconds. Okay, what's your answer? B. Okay. So here is another picture yet of those concentric rings, so onion rings, right? So the onion rings that are part of this osteon, of that little straw, you call them concentric rings. So the layers, the lamella, they call them, like, of course, lamella, you call this one's concentric lamella, or onion rings on the osteon. Now, if you look at other places, like between the osteons, you still have those layers that you can't really call them like onion layers. They're just like there, and they're kind of a bit disorganized. They're like between the different osteons. So you call those interstitial lamella, okay? And they also they show up also because of bone remodeling, okay? Besides those, when you look outside of the bone, which is not shown here, but let's assume at the periphery of this bone, of this long bone, you're going to have some very large layer, like one layer that is going around, one lamella or two lamella that's going all around the bone. So those are called circumferential lamella. Okay, so three types of these lamellas that you're going to find in the hard bone. Okay. Where you're going to find circumferential is very, very close to the membrane of the outside of the bone. So it's very, very close to the periosteum. Okay, so it's very close to the periosteum, and they're going to be also very close to the endosteum. So those are all called circumferential lamella. Okay. So looking here at the spongy bone. So yeah, it looks like a sponge, but it's not soft. It's very, very hard, just like the hard bone. Okay. Now, when you look at this at first, you might think that this is all a mush of disorganized structure, but that is not quite the case, because each one of those structures, which you call these things here, you call them trabecula. Okay, so those are beams that are strategically placed in places that you would get a lot of tension. Okay, so they really work like support systems for this bone that can really receive pressure from many sides. So when you compare this to a hard bone or to a structure of the osteon, you see that with the osteon, it's mainly the main purpose of osteon is to receive pressure in one direction like this. So if you try to press on the osteon, oh good, I have structures here too. Each one is osteon, so you put them together like this, and you press on it, you're going to see that it's very resistant to this unidirectional force. Now, if you hit it from the side, it might break, right? But if you press it up and down, you're not going to get the straws to break. Now, when you look here in comparison with the spongy bone, you can press from all sides, and this thing is going to be resistant. Is going to stand the pressure from many sides. Okay, from all directions. Okay, so the structure of these beams here, those are called trabecula. Okay, so you do not see osteons, but you do see these types of lamella that are within this trabecula. Okay. And still, if you're going to see lamella, you're going to see cells that are communicating with each other via those canaliculi. So you're going to find like laguna, you're going to find the lamella. You're just not going to find the osteon itself. Okay. Transmission of the weight in one direction, you would crack the bottom of this bone. So when you get to this side that you have to distribute the weight, you're going to find also the distribution of the weight through those lamella that is found in the spongy bone. Okay. All right. So here is a picture showing you that all bones are going to have the two types of bones. You're going to have, yeah, as you see here with a flat bone, you're going to have a layer of dense bone or hard bone here, and then the inside is your spongy bone. So compact bones on the outside, spongy bone on the inside. Okay. All right, so chemical composition of the bone. Okay, so you're going to have organic compounds and you're going to have inorganic compounds. All right. The organic part of it is going to come from the cells that are putting it out there. Okay, what kind of cells are involved here? Well, we say you have your osteogenic cells, your osteoblasts, or the osteocytes. Okay, you have those bone lining cells, and you have the cells that are breaking down the bone, right? Okay, so all the bone cells that are involved in there, they can deposit stuff in the matrix, and those are your organic components, right? They are going to make up the osteoid, so that basically is part of your bone matrix. Okay, so organic part of the bone matrix is called the osteoids. Okay. The osteoid, mainly secreted by osteoblasts, but they are maintained by your osteocytes. Okay. What you're going to find in there, you're going to find your collagen fibers. Remember the percentage of collagen fibers that you find in the matrix? What is the percentage of proteins that is collagen? 90%, so it's a lot, okay? So you have the fibers, and remember that these fibers, especially the collagen, is very important to give strength, they call here tensile strength, to the bone. So basically it's going to give some level of flexibility to the bone. Okay. The analogy that we have here is that when you are building, let's say you're constructing a building, you cannot just use concrete, right? You're going to put steel rods that are going to hold the concrete in place. Why? Because if you do not use steel rods, then if you put any pressure on the concrete, the concrete can crumble. But by placing steel rods together with the concrete, you can give it some tensile strength, that you can give it some bending capability. Okay. All right. So here, what is important to know here? Okay. Yeah, you have some of those protein fibers that you call them sacrificial bones. These bones are really intended to break when you put too much stress or too much twisting in the bone, but they are meant to break like that. So you call those important type of breaking of those bonds in order to diffuse the initial force that was applied in the bone, and also to keep the entire bone structure intact. So let's see here. So those are your organic components. Now, when you look at inorganic components, the main thing that you have to remember is hydroxyapatite. And those is not only one, there are actually several. And those are really the mineral salts that are deposited in the bone. So those are going to make up most of the mass of the bone. Okay, look at this, about 65% of the mass of the bone is made up of those hydroxyapatites. And you're only going to find them in bone tissues. Okay, so when you hear hydroxyapatite, you automatically should think bone. And where else are you going to find it? Like basically nowhere else in normal tissue. You're only going to find it in the bones. Okay. Most or a lot of those hydroxyapatites are made up of some calcium crystals. Okay, so that's your calcium deposit. And those are really placed around those steel rods. Those are your collagen fibers. Okay, so presence of those hard minerals is really what makes the bone hard. Okay, the bone is gonna be resistant to pressing or to compression. Yes. you're going to find them being dissolved. But when you look at tissue and you see hydroxyapatite crystals, that's going to be in your bone. But once you dissolve them, they go into solution. So you're not going to really find the crystals. You're going to find, derivatives that are going to lead to calcium. Yeah, you really don't want little crystals of bones floating in the blood. That can clog the arteries. That can be really bad. Okay, so no crystals in the blood, only in the bone. And I believe you don't even have hydroxyapatite in the teeth. You only in bone tissues. Okay, only in bones. Okay, but that was a good question. Okay, so those crystals are basically what make the mortar, right, of this construction here. Okay, it's capable of storing calcium minerals. Let me go back to here. But the bone, okay, you can also have some magnesium storage and some fluoride storage, but the bone can also store some ions or some metals or some other components that are toxic to the body, and they're not supposed to be there in the first place. Like, for example, when you have some type of lead contamination. Have you heard of paint, like used just to paint the walls, like the old style paints that they used to contain lead, right? This is very toxic to central nervous system. And it was one time, like, children would get intoxicated by, putting those chips of old paint in their mouth. And we know that the lead is going to go to the nervous system and interfere with normal nervous system function. But the bones are also going to absorb some of that toxicity and store the lead, okay? And that is good in one sense, that your brain did not get all the lead deposit at once, but it's bad in another sense that if you try to clear up your system from the lead, you're still going to have your own deposit of lead that got stuck in the bones. So as you go through bone remodeling, which takes a long time, right? As you go through bone remodeling, that is going to be liberated from your bones and it's still going to end up in your central nervous system. So this is why it's so difficult and it's so detrimental to be exposed to this type of toxic chemicals. Okay. All right, so here we go through this part that it always gives us a hard time, okay? So you're going to look at ossification. It's also called osteogenesis, right? So this is how you make bones. When do you start to make bones? Well, in utero at the very early stage, even before you leave the first trimester of pregnancy, right? There are 3 trimesters in the pregnancy, right? So around 2 months of in utero life, the baby starts to make bones, okay? And the process keeps on happening until you reach your height, your adult height, okay? Now, after you start building up the bones, you're going to be maintaining the bones throughout life. So you never really stop the process of bone remodeling. And you don't want to stop the process of bone remodeling, right? Otherwise, you lose the bone. All right. So here, around 8 weeks after egg fertilization, okay, you're going to have some membranes that are going to form in certain places, and you're going to have formation of cartilage in other places. So you're going to see membranes forming around the head area. Okay, so head, basically all of your flat bones in the head, they are going to derive from the membranes. Everywhere else in the body, okay, head and clavicles. You know where the clavicles are? Well, if you don't know yet, you're going to find out later. Okay, so clavicles. So clavicles and skull, those are derived from fibrous membrane. Everywhere else in the body, you're going to have cartilage that is going to show up, and especially hyaline cartilage. And that cartilage is going to give rise to the formation of bone tissue. It's not like the cartilage is going to be transformed into bone. That's not going to happen. Yes, you have a question? No? Okay. So cartilage doesn't get magically transformed into bone, okay? The cells don't just become like, oh, I'm a cartilage now, but I'll decide to become osteocyte tomorrow. That's not going to happen. The cartilage cells are going to die, and then bone cells are going to go to the place and make the bone tissue, okay? So two things are going to happen here with your hyaline cartilage part of your skeleton. Now, when you look at your at the skull and clavicular bone that are coming from the fibrous membranes, then you skip that process with the cartilage in the middle. You just go straight from membranes to bones. Okay, it's a bit of a simpler process. All right. So that means you have two ways of making bone. The first one is called endochondrial ossification. Chondria has something to do with the cartilage, so this is inside of the cartilage type of ossification. Okay. The second one is called intramembranous ossification. So two types of bone formation. Okay, so here we go with the fun one, with your endochondrial. So let's see what happens here. When you have this fetus developing, right? This is around week 8 or so, right, of pregnancy. Another thing also, this type of bone formation happens a little bit before the intramembranous type of ossification. So this can happen, I would say, like 6 weeks after a fertilized egg gets fertilized, after the eggs gets fertilized, and the intramembranous would happen after 8 weeks. So there's a bit of a gap between the formation of these two types of bones. Okay. So now, when you're having your fetus developing, or actually you have your blastula developing, if you have seen embryonic development in your endosome, endoderm, mesoderm, and ectoderm, right? So these things are coming from your mesoderm, from the middle part here of your blastula. Okay, so here you have your mesenchyme, and the mesenchyme is going to start making this type of model of cartilage. There is going to be basically like a rough idea of what the bones are going to look like. Okay, so here I have a depiction of the ectoderm, so that's the skin. Then after the ectoderm, you're going to start having the mesoderm. So you're going to have some loose mesoderm, and then you're going to have more condensed or hardened mesoderm. And from this hardened mesoderm, you're going to have this initial formation of hyaline cartilage. And then you look at this, yeah, you're going to say, oh, it looks like a little hand. Well, that's your humerus right there, and then radius and ulna and the little bones of the fingers, but you don't really see fingers. You didn't have apoptosis of those tissues happening yet, because this is only a few weeks after fertilization. Okay, so now you start getting cartilage. So cartilage is gonna something is gonna start happening with the cartilage. Remember that here, if you look at a piece of the cartilage, okay, remember that cartilaginous tissue does not have blood vessels, right? And the cartilaginous tissue, it also has this outer membrane, right, to keep the cartilage in place. And the outer membrane is a connective tissue that actually has the nutrients that are going to be diffusing to the cartilage. So you look here inside of your hyaline cartilage, and you're going to see that you have cells that are dividing, and they are depositing the cartilage gooey matrix around. And the matrix is not very friendly to diffusion, right? So cells that are closest to the nutrient source, closest to the outside here of the cartilage, those cells, they start to differentiate into endochondrial cells, right? But they have nutrients here, and as this cartilage grows, the cells that are more to the inside, they are still capable of dividing. Cartilage is always capable of growth, but those cells do not have a good supply of nutrients in comparison to the ones that are close to the border. Okay? So let's see what happens here. Okay, no blood cells inside here. So whatever those cells are getting, it has to be through diffusion. Okay, and then this thing looks like jello, so some diffusion is going to happen. Okay, but not for a long time. Okay, so the inside of this cartilage, you're gonna have cells that start to become unhappy. Okay, because those cells are not really getting the diffusion that they need to support cell growth and cell division. So these cells here, they start to upregulate genes that are not very helpful. They start to make a calcified matrix, meaning that they start to put calcium crystals in the matrix here, and it's going to make it the environment even less friendly to diffusion. It's going to make it more impossible for nutrients to get there. Okay, and then something else happens. Those cells, they start to atrophy. They start to enlarge because they are unhappy. They are not getting the nutrients, and they are putting stuff out there that is not being very helpful. So they are thinking that they want to die. They're really, really unhappy. Okay, and then on top of that, at the outside here, close to the periphery, this tissue at the membrane here, this tissue starts to make a type of a collar around it that is made of bone. So here it's showing only on this outside edge here, but imagine that this tissue is going all around this center cartilage. So it's not like only the edges are getting this bone tissue. All the outer shell is getting this bone tissue. Okay, that's why it's called a collar. Okay, so the construction of the bone over there is going to make it impossible for nutrients to go through. So these cells that are right in the center, they're really going to be unhappy and they're going to start dying. Okay, but they already had started to deposit some calcium crystals, or so they started a mineralization process. Okay, so you have some hard stuff forming over there. You don't have nutrients coming through the sides. These cells are dying. But then look at here. At the epiphysis, you don't have the collar, so cartilage is still okay over there. Okay, they're still getting nutrients like from other sides. It's still fine. Okay, so inside of the tissue, this thing is dying, and then look what happens. You're going to have in one side of this bone, you're going to have a foramen that is opened, so a blood vessel will penetrate, and it's going to go to the inside where you had the initial calcification right there. Okay, so here we're showing like before this blood vessel penetrated. Here we're showing after it penetrated. So once you have these nutrients coming with the blood, you're going to have stem cells that are going to get to those places, and they're going to start differentiating into osteoblasts. Okay, so your cells here, they were chondrocytes, they died. Now you're going to start placing osteoblasts, and the osteoblasts are going to start to make the bone matrix. And this is how you start to get this initial spongy bone type of formation from the inside of the cell. So here, this site here, initial site of bone formation, you call that your primary ossification center. Okay? Remember, you have this bone collar all around it, this really covering all the outside of this bone here. So here, the only place that you're going to get nutrients is through this artery. Okay, so that's your primary ossification center. Now, together with the stem cells that got differentiated, this blood vessel also brings your osteoclasts, and then the osteoclasts start to eat up and dissolve the spongy tissue. Okay, so first you build it and now you're breaking it down, but you still have a spongy tissue that goes around the periphery here. But the center, it becomes hollow. Okay, so this is going to be your medullary canal of your long bone. Okay, so this is really at your primary ossification center. Okay. Okay, so after that, you're going to start to build here your compact bone on the sides, and you keep some of that spongy bone in the center. And at this stage here, you're going to have one area close to the epiphysis. You're going to have one area that is not covered by bone. So this area here that is between your diaphysis and your epiphysis, this area here is still cartilage. So you call this area the metaphysis, is in the middle of your diaphysis and your epiphysis. All right? And this is actually the area that can grow in your long bones. So you have one on the top, one on the bottom. All right? So this is not going to be calcified until the person stops growing the long bones. Okay, so if you look at the X-ray of a child, you're going to see area, this metaphysis area, that is really clear. So you see that the child is still growing. Am I running out of time? Okay, so you have like 10 minutes. All right, so here. At this stage, when you have the primary ossification that happened, you're going to have another ossification that's going to go on at the epiphysis, right? So you're still going to have a little color of bone that is going around here, and you're going to have the same story that happens here with those chondrocytes that die, and then you have this other foramen. So those are secondary foramen that will go into the center of this ossification, and the same process is going to happen. You're going to start making the spongy bone at these secondary sites. So those are your secondary ossification sites, okay, at your epiphysis. Okay, so here I just put into words what I just mentioned to you. So I'm not going to go and read this stuff, okay? So this starts around 2 months of age. And at first, you're going to get the breakdown of the hyaline cartilage, okay? And stem cells are going to go there because you're going to have this artery that is going to go through the primary foramen. Okay, so here one thing that I didn't mention, let me see here. Okay, all right, so before those chondrocytes die in the middle of your hyaline cartilage, they start to deposit those salts, those calcium salts, and they have an enzyme that is very much important to form this calcification of the ground matrix. Okay, so that enzyme is your alkaline phosphatase. Okay, so ALP. So that enzyme helps with the deposition of calcified crystals. All right, so here you can read what I just said. And all right, so I just mentioned that. I don't think I meant anything. Okay, I mentioned all of this. You can read and review it. I just mentioned here your metaphysis, right? So when the person is growing, and you can actually see the cartilaginous metastasis, you call this area here the epiphyseal plate. Okay, epiphyseal plate. So this is when a person is growing. After you stop growing, you call that the epiphyseal line. So everything is going to be calcified, but this area here is going to be visible that it was, was a calcified area from a different origin than the rest of the bone. Okay, so here, okay, I mentioned all that. Secondary ossification. One important difference between your primary and your secondary ossification, you are not going to dissolve this spongy bone that you made at first. So the epiphysis will keep the spongy bone, okay? So at the epiphysis, you are not going to find this center canal. So no medullary canal at the epiphysis, at both of them. Okay, and then at the top of this epiphysis, you're going to find hyaline cartilage that is still going to be there and is going to be very useful for articulation for your joints. Okay, so here is just another picture showing the same thing. Okay, and now a little bit about your intramembranous ossification. It's not as complicated as as the one that is coming from the cartilage. Okay, so what is going to happen here? At each one of these bones, like what bones? The bones in your head, as you're going to learn them, you have your frontal bones and parietal bone, occipital bone. You're going to know where all of those are, right? So all those flat bones here, they start from between two membranes, okay? So each one of those bones is going to have one center of ossification, okay? So you have those very, very hard fibrous connective tissues, so very fibrous connective tissues, and you're going to have placement of stem cells. They are going to go in there, and they are going to differentiate into osteoblasts. Remember, blast is the baby cell. So stem cells get there from the blood, they get there, and they decide to become osteoblasts, and they decide to make the matrix, right? So they're going to be building up the matrix. So those guys here are your osteoblasts. They do not look like osteocytes yet, right? The osteocytes have the tentacles and they're not as fat, okay? So these guys here, they start to deposit the matrix right here, and they start to differentiate, and this is happening between two membranes, okay? So as these osteoblasts deposit the matrix and differentiate, they are making the wall. As they are making the wall, oh, here is not very evident that they are still holding hands, but yeah, they are still holding hands, because imagine that if they build the wall and they are not holding hands through those canaliculi, they're not going to break through their wall to get the hand of the next neighbor. Okay, so it would be like breaking the brick wall to try to reach your brother's hand in the bedroom when you are stuck in the kitchen, you know, with all mopping around. So, you have to have those canaliculi being there before you form the lacuna, okay? So they keep the connection here. So they are differentiating, they're still stretching their arms, they're still connecting, but they're building this wall all around, okay? So the ones that are to the inside of the bone, those are going to become your osteocytes. The ones that are close to the surface or to the outside, they keep on being osteoblasts because they have plenty of nutrients that are coming from the outside. Okay, so they have plenty of supply. They don't really start to get skinny and differentiate some more. Okay, so around the outside of the bone you have your osteoblasts. Inside of the bone formation you get your osteocytes. Okay, so out of that one site of ossification you are going to get the formation of your spongy bone, and then close to the outside you're going to get formation of your compact bone. Okay, so let me see what else is important here. Okay, so I mentioned that. So this is just a bit more of a description saying that at first you don't have the spongy bone as we know it with the trabecula. You have this thing that is called woven bone or primary bone formation, and as the bone evolves, further differentiates, then you replace that with your trabecula. And within these spaces, it's not like you're going to have empty space. You're going to have it filled with bone marrow. Okay, so in all of your flat bones, you are going to have bone marrow. Inside of the bone marrow, you're going to have your hematopoietic stem cells. So all the cells that are going to form blood cells are going to be placed there. But during embryonic development, you don't have your bone marrow there developed yet. Because remember, this thing is getting blood to go and bring your stem cells there and start this differentiation. So you don't have anything in that, right? So where is it you're getting the blood cells from? There is blood over here. There are blood vessels bringing blood, bringing stem cells. Where is the blood? Where the blood cells are coming from? Red blood cells. White blood cells? Any blood cell? Anybody knows how the fetus will make the red blood cells? Take a guess. They don't have bones. Yeah. No. No, but that was a good guess. Because you're thinking, this thing is developing inside of the mother. Maybe the mother is just donating some cells. No, because it's the different genetic material. Because with the baby, you're going to have your chromosomes also from the father. So it's not really compatible to just put your mother cells in there. So the baby has its own cells. Something is making the blood cells. Where? Guess some kind of organ. If you have to guess an organ, what would you guess? Okay, heart. That's a good guess, but it's not the heart. The heart is just pumping. The heart is just a pump, not involved with metabolism. Another guess. Let's eliminate organs. Huh? The what? Stomach. They would eat the red blood cells there and digest them, but no. The liver, yes. All right. You got scared with that one. You were like, the liver's like, yes, they're like, oh, she's gonna eat me. No. Yes, it's the liver. Isn't that weird? The baby is gonna make the blood cells using the liver. Yeah, and then after the baby is born, what starts to make the blood cells? The bone marrow. Because at that stage, the baby already has the bone that is formed. So the job shifts. Then the liver is going to have to deal with other stuff like metabolism or things that the baby will eat, right? You have to go through the liver and absorption and all that kind of stuff. But it's interesting how these functions will shift, right? From belly to outer belly. Okay. All right, so let me see here. We finished this. Intramembranous ossification. Make sure you understand the two different types of ossification, right? I know intracondylar is a bit more complicated, but yeah, if you visualize what is happening and how the cells are being, going through a stage of apoptosis and then being substituted, I want you to get there. Okay, before you go, one last question so you can get one more point here. I am going to put my little selection. Okay, come on. Confidence level is on. All right, so let's see here. It is starting. Okay. The principal component of bone that contributes to its hardness. Oh, come on. Everybody gotta get this one right, especially because I think I had the answer there before. If I say this word, you think bone. So give me the right answer. Nowhere else in the body you're gonna find it. 5 seconds. All right, what's your answer? Hey, yes, your hydroxyapatite. Okay. All right, so I'm going to stop here and we pick up on Wednesday. Do we have questions?